So what we are talking today, really, the whole lecture today is all about reflection of radio waves. We have many different examples of reflection of radio waves. The first hour was devoted to reflections of mirrors on mountaintops, say to cover to recover from the huge diffraction loss just off the mountain ridge. We could install a specialized structure to improve this diffraction, or we could install a mirror, so use a reflection of radio waves. But there are also other possible uses of reflections, and we are going to talk about them. And this hour, I hope to conclude the issue about aircraft radar. So what is this all about? I have one antenna connected both to the transmitter of the radar and to the receiver of the radar. And this one antenna transmits towards an aircraft that's supposed to be a non-cooperating target, and I receive the reflection back. So this is also called a monostatic radar. Because both the transmitter and the receiver share the same location. Okay, I also have the other possibility. I have the possibility of a bistatic radar that has a separate antenna for the transmitter, and in some other place it has an antenna for the receiver. And the radio waves bounce off an aircraft. So this is also called bistatic radar. Bistatic radar can be built, but bistatic radar is very difficult to use. There are two separate devices you need to have at different locations, and for the military users, this is simply too complicated. But on the other hand, a very simple use of the bistatic radar is to arrange for long distance communication. Radio amateurs are using this in Europe because air traffic is very dense in Europe. You have lots of aircraft flying at around 11 kilometers altitude, and you may receive these reflections of the transmitted signal up to a distance of 500 kilometers. So covering 500 kilometers at microwaves, that's quite a good achievement. So this reflection can be used for other purposes, not for finding out where the aircraft are, but for making communications of these targets that are actually available most of the time over Europe. Europe has a very dense air traffic. So what can we say about the monostatic radar? This is the most usual form of radar. Okay, in order to calculate this link, we need the power of the transmitter, the minimum power put in the receiver. We need the gain of the single antenna we have, and we need data about what happens with our target. And with our target is described by an area that's called a radar cross-section. It has units of an area, so radar cross-section is given in meters squared. How is now defined the equation? What power do we get to the target? Power that's received by the target is now power of the transmitter times gain of our antenna, distributed over a sphere with 4 pi r squared, okay, and received by the radar cross-section multiplied by sigma. So if I look, this is meter squared, this is meter squared, cancel out, so the units are okay. It's assumed that if we provide the radar cross-section, assumes that the gain of the target is equal to 1. So this radiation falling on the aircraft is scattered in all possible directions uniformly. So it's an omnidirectional pattern. So the power in the receiver we get, power in the receiver, will be power on the target times gain of the receiving antenna. Gain of the receiving antenna is just gain because we have just a single antenna. So I need not write here, gain. Times this G target that's equal to 1. And the equation lambda over 4 pi r squared to complete the Friis equation. Because the gain of the target has an according to the definition of the radar cross-section, the target has an omnidirectional pattern. So we assume that the target has, it's scattering this transmitted signal in all directions equal. And now we can make the whole calculation. So what is the received power? Is now the transmit power. No, not the transmit power. Transmitted power. Power of the transmitter. We have G squared. Because the gain of the antenna accounts both in the transmission and in the reception. So G squared. We have here 4 pi to the third power. We have r to the fourth power. We call it r squared here and r squared here. We have lambda squared here. And we have our radar cross-section sigma. So this is now the equation of our radar. People are mostly interested not what the received power is. This is known for the receiver. But what will be actually the range of the radar? What is the range of our radar? If I turn this thing back into the range, so if I rearrange the equation, so r is now the fourth square root. The fourth root, not square root, but fourth root, or square root of square root. Power of the transmitter divided by power of the receiver. G squared. Lambda squared. 4 pi to the third power. Sigma. We can find the range now out of our radar. Let's try an example. What the power might be. What are the issues that I have? The transmit power for pulses may reach 1 megawatt. 1 megawatt is not a particularly powerful radar because this is just peak power. This means 1 kilowatt average. 1 kilowatt average is not a particularly strong power. So I have 1 megawatt just in the peak, transmitting very short pulses and then having a very long period. And the power in the receiver, I can assume, say, 10 to the minus 12 watts, or say 1 picowatt. 1 picowatt. This in other units, this is also minus 90 dBm. Written in other units. So this is a typical figure for a receiver. So this is a P transmitter. 1 megawatt is transmitted for 1 microsecond, and period over which this pulse is 1 microsecond pulse, and repetition period is, say, around. It's usually more than 1 millisecond. So let's say it's more than 1 millisecond. That's the reason where the 1 kilowatt average power comes out. And this is not a particularly powerful transmitter for the radar. 1 megawatt peak, 1 kilowatt average. What is the gain of the antenna? What the gain of the antenna? The gain of the antenna, I assume the gain of the antenna to be around 40 dBi, or around here around 10 to the fourth power. Okay? So we have all the data for our equation, and we can see where can we detect our aircraft. So I can put all the other figures here in the equation, and let's see how far can we go with this radar. So we had 10 to the sixth power watts, 10 to the minus 12 power of watt, 12 power of watts. Watts, of course, cancel out. Then I have the gain of the antenna squared, so 10 to the fourth power, further squared. Lambda, what is the wavelength here? I need this data. Aircraft radar is usually such primary radars, so radars that actually do not use any cooperating target here. For aircraft usually work at a wavelength of 10 centimeters, which is equal to the frequency of around 3 gigahertz. Also, the radar on Ljubljanski Vrh above Vrhnika, if you ever saw the ball on Ljubljanski Vrh over Vrhnika, that's also 3 gigahertz, also a military radar. All of them have about the same, and this corresponds to a dish of about 3 meters diameter dish antenna for the given gain. So at least just to give you an idea how large the antenna is. So 3 meters diameter for a radar installation on a mountaintop is not that bad. So let's put all figures in our equation. We have here we have 0.01 meters squared, okay? And I have 4 pi to the third power. So 4 pi is 12.56, squared is about 150. Again, multiplied by 12, 150 multiplied by 12, we get around 2000 here. So 4 pi to the third power is around 2000. Just to make an approximation for this. 4 pi is, in decibels, is 11 dB. 11 dB 3 times, because in logarithms we have to multiply the value, is 33 dBs. 33 dB is 2000. Okay, that's my simple calculation. And we have sigma. We are left with sigma. So let's see what the range is going to be. Range is square root, fourth root, not square root, fourth root. So this is 10 to the 18, 10 to the 4 squared is, so this is 10 to the 18th power, times 10 to the 8th power, times 10 to minus 2, what we have here, 1 over 2000, times sigma. Just to make this meter squared. Meter squared, I can write it here, meter squared. I had it here, meter squared, times sigma. Now, just to keep calculations simple, a large airliner, this may have a cross-section, sigma, of approximately here 20 meters squared, okay? Just to keep the calculation simple. So let's see what I have here. I have, if I put 20 meters squared here, 20 meters squared, I have 18 plus 8 is 26, minus 2 is 24, and I have I'm left another one is 2, 10 to the minus 10 to the 22nd power of meters to the fourth power. Let's try to calculate now this. Square root is 10 to the 11th power. then another square root is 10 to the 5.5. So this is 10 to 5.5 meters. So 10 to the 5 to the 10 to the third power is kilometers. 10 to the fifth power is 100 kilometers. 100 kilometers times square root of 10, because 0.5, 10 to 0.5 is square root of 10, is 3.16, so is 316 kilometers. With such a radar, we can see almost any aircraft, considering also the Earth curvature, because the aircraft, the airliner is here at a height of 11 kilometers. We can reach 11 kilometers, we can see it at 300 kilometers range. So whatever is in our, in our visual range, we can see it with this radar. Not that good for other aircraft. So we will see how to derive this figure, now sigma, how to derive it out, how to get it out. Now here I just guessed this for an airliner. Airline aircraft. How to get the figure sigma, what the figure sigma actually is. You remember last hour we had a flat mirror. A flat mirror reflecting waves of the surface. So it has an A mirror here, reflecting whatever is falling on this mirror, reflecting back. What is the calculation now for sigma? First, the power we get, we had A mirror 1, so sigma here is surface of the mirror, this is the collected power by this mirror, times the gain of the mirror. The gain of the mirror, because this is an aperture that's illuminate all the single Huygens surfaces sum together. It's a uniformly illuminated aperture, and so this gain of this mirror is now 4 pi over lambda squared times A mirror. So the sigma of a mirror may be pretty large. So it's 4 pi over lambda squared times the actual surface of the mirror squared. So even though sigma has units of area, we actually have the area of the mirror squared, because if we increase the size of the mirror, we both increase the power collected by this mirror, and we increase the gain of this aperture. So the A of mirror has to play a role twice here, so having the twice or squared here. So the effective, the radiation cross-section of a mirror may be very large, but this is just one direction. And we have quite a difficult work to adjust this mirror, say, like I told you the previous hour on the mountaintop, when installed on the mountaintop, it's very difficult to adjust this mirror. What can we do to have a better reflection of a mirror in the same direction? If we are talking having the largest cross-section in the same direction. Or in other words, making a device that will be very well visible on a monostatic radar. How to make a reflector? And the idea is to use a corner. So you have a right angle corner of two mirrors. No matter where the radiation comes from, it will be always reflected exactly in the same direction. This is true in 2 dimensions. In 3 dimensions, we need a cube corner. So in 3 dimensions, I put in 3 mirrors. Now it's very difficult to draw this on a 2-dimensional board. I draw this cube corner. Has 1 mirror, another mirror, and a third mirror. And I have right angles between all 3 mirrors. And the cube corner will always reflect the incident radiation exactly back in 3 dimensions. So I have first reflection, second reflection, and third reflection. Exactly. So each of the reflections changes the sign of one of the components of the wave vector. If I change the sign of all 3 components of the wave vector, then I have the reflection exactly in the opposite direction. This is the trick. So put this thing in a Cartesian coordinate system, x, y, and z. So which here I flip the sign of the ky. Here on this area, I flip the sign of kx, and here on this area, I flip the sign of kz. If the wave vector is now kx, ky, kz. So I can flip the sign of the whole vector by flipping the individual signs of the individual components of the wave vector. So I obtain a 3D back reflection exactly in the direction back. So where are such reflectors used? They are used both in radio and in optics. Maybe the most familiar you are in optics. In optics, corner cubes, where are they installed? They are installed on all traffic signs. They are installed on the marking in the corner cubes are installed in the markings of the paint on the road. So the road the paint of the road signs look like white, but they include crystals, cubic crystals that reflect the light waves exactly in the opposite direction. They are also installed, cube corners are installed in the license plates of cars. Have you ever taken the picture of your car at night when the flash triggers on your camera? What do you see on that picture?
Light.
Just the license plate, nothing else. Because the license plate reflects all the light of your flash of your camera exactly back to the camera. And at night, if you take the picture of your car at night, you will only see the license plate of your car. Also, the policeman, when with his laser gun, he measures the velocity of your car, he's actually targeting the license plate of your car because he has very good reflection of the license plate of your car. And that's the reason why you are not allowed to paint your own license plate, because that one is not going to reflect the light of the laser gun. They are also used in radio. They are used on boats. If you look even at sailing boats, so if I draw here a sailing boat, you will see that the top of the mast of the sailing boat, up here, you have such a cube corner. And this cube corner, what is its purpose? Its purpose is that you can see this sailing boat very good on maritime radar. Say big ships have radar, even a little bit larger yachts do have radar on board, and they can see you on sailing boat, and they can avoid your sailing boat by seeing this target on your radar. This may, even though this is maybe 10 centimeters large, the area becomes very large because the wavelength of the radar is very short. The maritime radar is around 3 centimeters. So if you have 20 centimeters here, I already have 10 lambda here. I already have multiplied my radar cross sections by a factor of 100. So this is a very efficient cube corner. Even on sailing boats, you may have 3D reflectors. This is a 3D reflector. You may have also angled strips at right angle, just 2D reflectors, because all the radars you can expect here always come from the horizontal plane. It's not necessary to correct for the vertical component of the for kz. It's just enough to correct ky and kx to have the reflection. But you can have also this, and this is usually packed, these reflectors are usually packed in a tube so that they don't get broken, and this tube is installed on the boat, on the top of the boat. So this is something that's practically used. So this is actually a cooperating target here, a cooperating target here. With a cooperating target, I can have a very large radar cross section. Somewhat different is an aircraft. An aircraft, usually its shape is defined by the aerodynamics, not the form. So I should look for other targets what happens. And I will do now my example. If this is the radar antenna, of a sphere, a perfectly conducting sphere. So a metal sphere. And let's this metal sphere make it much larger than the wavelength. So the radius of this sphere, the radius A of this sphere, let's say it's much larger than the wavelength. What do we see here? If I transmit anything from my radar, I could depict on this surface Fresnel zones. But Fresnel zones are not dictated by just the difference from the radar. Fresnel zones are also dictated by the curvature of this sphere. And how large will the first Fresnel zone be? So the first Fresnel zone, if I draw it here, the first Fresnel zone will be its height, h, will be equal to lambda quarter wavelength. Because in this way, I have quarter wavelength more path here and quarter wavelength back. So for the reflected wave, the reflection of this Fresnel zone, this is actually already a flip of phase of 180 degrees. It's we have very little flip because of the changing distance from the radar. I have a very big flip because of the curvature of the ball. So what is going to be now the cross section of this metal sphere? Of course, the metal sphere, because it's round, also scatters radiation in all possible directions. But for us, for a monostatic radar, it's sufficient to know what comes of this first Fresnel zone here. Now, I should see what is the area of the first Fresnel zone. So, the area of the first Fresnel zone here, what does it is? It's actually, if they have the area of the first Fresnel zone, actually covered the first Fresnel zone, and just off the first Fresnel zone, how much field do I get? I get twice the field of the whole mirror. If I had here a flat mirror, infinitely large flat mirror, of the first Fresnel zone, I actually get twice the field. You know, you remember when we only had the first Fresnel zone open in our obstacle, we got twice the field. The integral got to twice the field. Twice the field means 4 times the power. And that's the reason why this is 4 times the power. What is the area of the first Fresnel zones? The area. The area of the first Fresnel zone is actually rho 1. What is now rho 1? Calculated here, if I draw the triangle, this is A, the radius of the ball. This is rho 1, is a right angle, and this is A minus H. Okay? So the area of the first Fresnel zone, is now pi rho 1 squared. Because we're looking at the first Fresnel zone. And I should get rho 1, what it is. According to Pythagoras, rho 1 is now square root of a squared minus a minus h squared. Okay? And if I calculate this, this is now square root of, because of this minus sign is 2 times a h minus h squared. Now, rho 1 squared, what it is? Rho 1 squared is now this thing without the square root, 2ah minus h squared, where I know what h is. And I know that H is now much smaller than A because of my requirement up here. So I could neglect this thing here. So this is now approximately pi times 2AH, where I know what H is. A of the first Fresnel zone is now pi times 2A times, I said it here, 2A lambda fourth. Area of the first Fresnel zone. And now I could 2AH, yes, I still miss something here. Maybe I was just too quick for the area of the first Fresnel zone I have here. I calculated rho 1 squared is without the square root, and I put here lambda squared. So this is now no, this is probably wrong. This is wrong. I was slightly too wrong here. Area of the first Fresnel zone here I have, and now I should calculate the actual sigma of the first Fresnel zone. Yes, that was correct. That was correct. Sigma of the first Fresnel zone was correct. No, this was correct. So I just missed 1, 2 here. One factor of 2. I missed it here. I lost it somewhere. So sigma of the first Fresnel zone. Sigma of the first Fresnel zone is now, yes, I should use this equation here, 4 pi over lambda squared so times, this is the correct formula, area of the first Fresnel zone here. Okay, so now if I put squared, because I look at the first Fresnel zone as a flat area, and sigma of the first Fresnel zone now is 4 pi over lambda squared times, here I have area, this area is now pi times a lambda half. And if I square this now, thing now is pi or times a lambda half squared. I still miss something here. What I forgot here is we should include that this summation here is over the first Fresnel zone, no over a flat mirror. So we have a sum of going through along a semicircle in place going the right line. So here we have still this factor 2 over pi squared. 2 over pi squared. So the area of the first Fresnel zone is now, if we had just the first Fresnel zone, pi cancels out, lambda cancels out, so lambda squared cancels with this lambda. Pi cancels with this pi, half cancels with this half, and I am left with 4 pi here a squared. But we said that for the whole sphere, now for the whole sphere, we have many Fresnel zones here. So we actually have the integral making this. We get half the field or 4 times less power. So the whole sphere, its sigma, will be 1/4 of the surface of the first Fresnel zone here. And 1/4 is exactly equal to pi a squared. So this is a very simple result for the sphere. I should have considered here that the reflection is not of a flat mirror, but of the first Fresnel zone. This was the thing I forgot here to tell. This was other. I forgot this factor here because it's the first Fresnel zone, not the flat mirror. 2/pi is exactly the ratio between the diameter and the circle, and the semicircle, half of the circle of the summation. So for the sphere, we know very well, for large spheres that are much larger than lambda, we know very well what their radar cross-section is. So what about our aircraft right now? Our aircraft, if I look it sidewise, the aircraft here it has wings, it has engines below wings. Where do I get reflections for the aircraft? I get reflections of a nose, I get reflections of the engines. And I should put my sphere in here, and I should put my sphere in the engines. If I look on the aircraft from the side, so if I look it in this direction, I transmit with the radar in this direction towards the aircraft from this side, or let me draw the aircraft once again up here. Okay, maybe I can draw it here. So if I draw the aircraft in this direction, wings, tail, engines. Now, where do I get reflections? I should put spheres in here, spheres in here. Maybe something on the wingtips, but that's very little. The main contribution is here and here, say from radiation coming from the side to the reflector. And here from the side, because this area is quite long, here I may get a sigma of around 20 square meters. Here in the front, I maybe get sigma only less than that, maybe sigma only around perhaps 3 square meters, depending now on the size of the aircraft. This is for civilian aircraft, so I know that this equation is approximately correct. And you see that sigma only takes place under the 4th root. So even if I change sigma by almost a factor of 10 here, the 4th root of 10 is 1.7. So you get very little range difference. Now the question is how to make an invisible aircraft. Where is the eraser? Here. How to make things invisible on the radar? The idea behind making things invisible is having no vertical flat surfaces, because this is actually the first Fresnel zone is actually here and here on the engine. Having no flat surfaces, this is not according to the aerodynamics requirements, but having no flat surfaces. So making a military aircraft, what is the idea? Have all surfaces sharp, like this. Have everything sharp, so that the sphere I install here in the nose of such an aircraft has a very small radius. Also from the other sides, when I view it, the sphere is very small here. That's the idea behind building an invisible aircraft. How low can we go with this aircraft, with this visibility for such an aircraft? We can get down to sigma between 0.1 up to 0.01 meters squared. What is then the range of our radar here? If we go to such small values, here I had 20 meters. I have the area that's 1,000 times smaller. Taking the 4th root of 1,000, the square root of 1,000 is 30. It's around 5 times less range. So here maybe I can get down to a range of around, say, 5 times less, 360, is around perhaps around 60 kilometers. With such small cross sections, with the smallest one, so 60 kilometers is here for the smallest area. It's not really invisible, just the reflection is small, but remember the fourth power of the square root. The fourth power of the root is not a square root, it's just the fourth power. The 4 is also missing here. The fourth root really brings these differences down to very small values. Further, these things are only valid when our sphere is much larger than the wavelength. So these things are only valid, and most such invisible aircraft are only designed for the wavelength of the anti-aircraft rocket, and this is for lambda around 3 centimeters. So if you fire a rocket towards an aircraft, that rocket has a radar operating at 3 centimeters. Even if it may not have a whole radar on its own, it may be the the chasing aircraft launching a rocket may have a radar illuminator, and the rocket just receives the back reflection of the radar. So only for radiation coming from this side and coming from this side. Then the radar cross-section is very small. And for the correct wavelength. Where are these such an aircraft designs very inefficient? Such aircraft designs, they may have also some paint. So paint of this aircraft may have a gamma of around 0.1. So another 20 dB is lost with a special paint this aircraft are covered, but only for a single wavelength, for the wavelength of the anti-aircraft rockets. If you look at this aircraft at longer wavelength, your sphere becomes like this at longer wavelength. And at longer wavelengths, you don't see the shape of the aircraft, you see the whole aircraft acting as a single sphere. And at longer wavelengths, such an aircraft has a much larger radar cross-section. So how to shoot down such an aircraft? First, you have to detect the aircraft at much longer wavelength. So if you remember 20 years ago in Serbia, when such an aircraft was shot down, it was actually shot down by Serbian radars. It was a technical achievement by the Serbian army at that time. And they first used, for initial detection of the aircraft, they used a radar at lambda around 2 meters. An old Russian radar, but very efficient for detecting such, say, invisible aircraft. They're not invisible. And in the second case, they shot a rocket from below. Shooting a rocket from below, you have an enormous reflecting surface down here from this aircraft. And here sigma may go beyond 100 square meters. So shooting the rocket exactly from below to such an aircraft, the rocket did have a radar at 3 centimeters, but it was shooting an enormous target from below. And that's the reason why they could shoot down such an aircraft. That was the reason why they could do it. It was a technical achievement. The officers of the Serbian army did understand how the radar works. The American pilots never understood this. Also, fourth power was missing here. Fourth power. Oh, so now what we want to do the opposite. You see that the detection of a civilian aircraft may be quite unreliable by such, we call this also primary radar. At 3 gigahertz. So this is very unreliable. Sorry, losing the time here, but I said that I have 2 longer lectures here. How to make this thing visible? This is not easy. How to make this aircraft visible for the traffic control? Because for the traffic control, yes, we see the radar. We see the aircraft that has a radar cross-section, say, of an average cross-section. Here's the radar. we shoot the aircraft with the radar, and the aircraft may have, say, an average cross-section of around 10 square meter. But behind the radar, behind the aircraft, we also see the mountain. And the mountain may have a radar cross-section here of around 10 to the 6th meter squared, 1 square kilometer. So how to separate the radar from the so-called ground clutter? Or ground. How to see actually with the, how to separate the wanted target from the unwanted clutter behind. It's easy. It's very easy. This shooting to an aircraft from below. From below, there are no mountains up in space, so the only reflection you have is of the aircraft. But in the real environment of civilian air traffic, you have this problem. How to solve this problem? You solve this problem with the Doppler shift. So if this aircraft has actually some speed, you actually get the Doppler shift. The Doppler shift, and this speed actually accounts twice. So the Doppler shift will now be equal to Doppler shift delta F will be equal to F0 of the radar multiplied here by twice V, the radial components of the V, divided by the speed of light. So using the Doppler shift, you can separate your wanted target from the mountain. The mountain has a velocity of 0. Yes, not really 0. Something is changing also in the mountains. You may have trees here, and these trees can be moving back and forth in the wind. So they do have some effect on the very strong reflection of the surface of the mountain. That's the reason why this velocity, in order to detect an aircraft, the radial component of the velocity, so this is 1r times vector v, this should be actually larger than for civilian air traffic 150 kilometers per hour. There are no mountains that are faster as that. So mountains are not detected by such a radar. Yes, helicopters are detected. Why is a helicopter detected? A helicopter is detected because the helicopter has a rotor that spins. And this spinning rotor is moving at a very fast velocity. So a helicopter, you can see it with Doppler shift because the helicopter may be just be at a fixed space, maybe just hovering at some fixed position, but its rotor is always spinning, so you can see the rotor with the radar. You cannot see very slow aircraft. You cannot see balloons. If you have hot air balloons, this is also V going to 0. Velocity of the balloon is also going to 0. You cannot see a hot air balloon, you cannot see it. You can see a helicopter, you can see a fast aircraft. You can also not see glider aircraft. Glider aircraft are slower than 150 kilometers per hour. So you cannot see several different kinds of aircraft with such a radar. The primary radar, I'll say it's okay for the military. The military always think about a non-cooperating target like this one here. But for civilian use, you have to use a pulse Doppler radar here, so transmitting pulses and measure the Doppler shift, and you only detect targets that do have enough Doppler shift on their frequency. It's not that easy to do this. This makes the primary radar quite unreliable. So what is actually done with civilian aircraft? With civilian aircraft is that you have cooperating targets. cooperating targets that here have on board both a radar receiver and a transmitter. So the radar actually gives a question at 130 megahertz from a secondary radar. And they get a reply from the aircraft at a different frequency at 1090 megahertz. This thing is already known dates back to the Second World War, when it was used and is still used for identification, friend or foe. This is to avoid shooting down your own aircraft. Detecting only enemy aircraft that don't have IFF. In the civilian aircraft, we have also such, this is called the transponder. And actually the question here is just 2 pulses at a known separation. And with the separation, it's 8 microseconds or 21 microseconds. This is mode A, mode C. Mode A was actually also used for IFF in the Second World War. All these things date back to the Second World War. So that's the reason why these frequencies are low for today's standards. And the reply we get, maybe A, it's between 2 and 15 pulses. It may contain A is ident of aircraft. And mode C is pressure altitude. There is further mode S. Mode S also has the same frequencies. This mode S has 56 or 112 bit frames. This is a more complicated digital communication. In this way, on the secondary radar, the flight controller may identify the aircraft. They ask the pilot to set a particular code in his transponder to reply with the correct code. And with C, it gets the pressure altitude of the aircraft, because the main way of collision avoidance in air traffic is to have aircraft spaced by altitude, not by position, horizontal, but by altitude, because altitude is known to a more correct information. In the same way, you also have such small secondary radar also installed on other aircraft. Other civilian aircraft also interrogate this aircraft here and get a reply back on the same pair of frequencies, and this is called TCAS. Traffic Collision Alert System. So TCAS, now all civilian aircraft in Europe above a certain size, not the small ones you get in small airfields, but the civilian passenger aircraft, all aircraft in the civilian air traffic in Europe have to be equipped with TCAS. So this is the main purpose of, you also have a small radar on the aircraft itself, and it does not have the range and the accuracy of the ground-based secondary radar, but it's enough to detect targets close by to avoid collisions. And it's also using this transponder on board the aircraft. So this is a quick way through all possible radars here. Now, in the next hour, we have to deal with reflections of ground. So we have a different kind of reflections. It was very difficult to describe all radars now in 55 minutes, what we did here. This was very difficult to do. And further, I forgot this factor here. 2 over pi, because a Fresnel zone is a factor 2 over pi over a round, over an in-phase reflection. I forgot this factor. Okay. Now we make a break and we continue with a completely different reflection. The reflections of ground. We will talk about a similar kind of radar is also the weather radar. We are going to talk about the weather radar in about 2 weeks. So next time or the week after next time. The weather radar has a little bit different equations, so that comes a little bit different. Is also the weather radar does not have the fourth power here. That does not come out in the weather radar. So we are going to talk that later on. Not today.